Welcome everybody to this new edition of our Cards Digital Thursday. The topic for today will be the Moldex3D FVA interface, and we will be showing that today in combination with Simcenter 3D. First, let me shortly introduce myself. My name is Vasco Keizer and I've been working at Cards for 5 years now. I mainly have a commercial role where I'm active in the Benelux, focusing on the simulation portfolios we have. So that's Moldex3D and Simcenter 3D. And presenting with me today again is Larry Wren from Moldex. So Larry, if you could also introduce yourself.
Hello everyone, my name is Larry. I'm the regional manager for the Benelux area inside Moldex. So today we're going to continue from the results from the previous webinars. So now we have a complete Moldex calculation, and then we're going to export the anisotropic material properties for NX to do some further analysis. Thank you, Vasco.
Okay, looking at the agenda for today, we are going to start with a short introduction. Then we're going to talk about the standard assumptions that are usually being made in a structural analysis. Then we're going to take an in-depth look in the Moldex3D FVA interface to find out exactly what it is and what it can do. And then we're going to end with a demonstration where we will be showing the entire process. But first, let's talk about the basics of injection molding simulation and structural analysis. Because we might have some people here who are purely focused on injection molding simulation, and we might have some people who are purely doing structural analysis. So when we're talking about injection molding simulation, we're talking about analyzing the plastic production process in order to spot potential issues like a short shot, like weld lines, air traps, or the final warpage of the part. And we do that by analyzing the different stages of the process. So we analyze the filling, the packing stage, the cooling, and the final warpage of the product. And it could be for a standard injection molding process, but it could also be for instance, compression molding, or foam injection molding, and so on. Now, when we're talking about structural analysis, we're talking about analyzing the structural performance of either a component or of an assembly. And we do that because we want to validate the design to make sure it doesn't break or yield, or we do that because we want to achieve maybe some lightweighting in the part to see if we can make it thinner. And we do that by analyzing the deformation and the stress that occur during some specific load case. That could be in a very simple linear static analysis, but it could also be in a specific simulation, like for instance a drop test or a crash test. In the previous webinar we already talked about the importance of warpage and how it, besides having a large effect on the product quality, also had a large effect on the structural analysis being done by the CAE department. So if you have some specific interest on simulating the warpage behavior of parts and you've missed this previous webinar, then you can find it back on our Cards PLM Solutions YouTube channel titled How to Improve Warpage with Moldex3D. Let's now talk about some of the standard assumptions that are usually being made in a structural analysis. When we're doing a basic structural analysis, we usually assume there's no initial deformation, for instance due to the warpage. We take the CAD geometry and we do a simulation based on that, and we assume it will be in reality as perfect as the CAD geometry will be. Also, in most cases you use a isotropic material, which has the same strength in each direction. Even when the material that's being used is filled with fibers, there usually is just a average value that's being used for the stiffness that kind of represents a random orientation. Also, the density is assumed constant throughout the entire part, and the assumption is being made that there are no local weak spots, like for instance due to molding effects like weld lines. And also we assume there's no initial stress in the part, so no residual stress due to the injection molding process. And of course, that's fine when we're doing an initial analysis and we want to get a basic gist of how the geometry will perform. Do I need to add an extra rib? Do I need to use another material? Then it's fine to do these kind of assumptions. But as soon as we're moving more towards really the validation stage, where we want to do a simulation as accurate to reality as possible, then of course these factors become quite interesting to take into account as well. And that is exactly what we can use the Moldex3D FVA interface for. Okay, so let's take a quick look at the Moldex3D FVA interface. As you can see on this slide, it basically stands between the injection molding simulation and the finite element analysis software. So on the side of injection molding simulation, you run your analysis as you used to. So you can just run a flow analysis, or you can run a full analysis including packing, cooling and warpage. And as soon as you're analyzing the results, you can open up the FEA interface. And there you can select the solver you want to export to. So it could be an ANSYS, an Abacus or an Alice Dyna. Or, as we're going to demonstrate in this example, NX Nastran, or how it's nowadays called, Simcenter Nastran, which is the basic solver being used on the Simcenter 3D platform. And basically what you're doing is you're exporting an input deck for the finite element analysis software that contains the material properties as simulated in Moldex3D. And then as soon as you import that input deck in the FEA software, you can then run whatever kind of analysis you want. So that can be a linear static analysis, could be a buckling analysis or a dynamic analysis, or it could also be a multi-physics analysis. That's up to the user. But now let's take a look at what we're actually exporting by using the FEA interface. The most important thing is that we're exporting an anisotropic material for specific regions of the part. So within that material, the effects of the fiber orientation is included, the different density throughout the part is included, and also local weaknesses due to, for instance, weld lines can be included. So if you have a local weld line, then for that local area, a different material card will be exported where the stiffness will be lower compared to the rest of the geometry. And on the right side you can see an example of how the density impacts the natural frequency of a part. In the results from Moldex3D you can see that the density is higher on the outside of the part due to the packing, and in the table you can see that on the left the natural frequency values when you use a constant density, and on the right you can see the impact it has on the frequency when you use the density at end of packing. And besides those properties, it's also possible to export the temperature output. So the temperature output at the end of packing or at the end of cooling. You can export the initial strain output, so the effects of the warpage and the shrinkage. And for some FEA software it's also possible to export the residual stress output. And that can be the flow-induced stress, or it can be the thermal stress due to non-uniform temperatures. Okay, now what we would like to show today in the demonstration is one of the possible process flows of using the FEA interface. Now in this case we will start within Simcenter 3D by setting up an initial baseline simulation using an isotropic material and analyzing the results. Then we will export a mesh file that can be used in the FEA interface from Moldex. At that moment, Larry Wren will take over the demonstration by showing a basic injection molding simulation with Moldex3D, and then using the FEA interface in combination with my mesh file to export a Nostron input deck containing the material properties from Moldex3D. And then in the final part of the demonstration, I will then import the Nostron input deck back into Simcenter 3D to run a second calculation with the material properties from Moldex3D, and then do a comparison between the two runs to show you the difference. But for now, let's start with the first part of the demonstration, which is setting up an initial calculation within Simcenter 3D of a basic linear static analysis, and then exporting a mesh file that can be used in Moldex3D. So here we see the NX environment, where I've opened the part we've also used in our previous webinars, and we are going to use this part to set up a first initial linear static analysis using the Simcenter Nastran solver. Now of course, in order to set up a simulation we need to take a few basic steps. And the first step I'm going to have to take is to create a 3D mesh based on my geometry. So in this case I choose an element size of 4 millimeters and mesh the geometry. And the second step is of course that I need to create a material for this model. And the material that we are going to use is the same material that Larry used within Moldex3D, which is a fiber-filled material. The only difference is that here the material is created as an isotropic material, which of course means that the fiber orientation itself has no influence. Now onto the loads and boundary conditions. First we are going to apply a fixed constraint on the bottom face. Then we are going to choose a specific constraint for this face to make sure it cannot move out of plane. And then for the loads we are going to choose a force load with a magnitude and a direction, which we are going to apply on the inner faces of this part. And we are going to apply a force of 100 newtons and specify the vector, which will be the C direction. That's basically all we need to define for this solution. So now we can click solve to calculate this model, and as soon as the results are done we can click on the results to open them, and we can look at, for instance, the displacement results, where we see we have a maximum displacement of just below 1 millimeter. And we can animate the result to get a clear understanding of exactly how the part deforms. Of course, this is an over-exaggerated plot. And of course we have some different results we can analyze, so we can also take a look at, for instance, the stress that is occurring in this part as a result of the loads. Now, after being done with the first calculation, I want to export this mesh file to Moldex. So I'm going to go back to my mesh file here, which is located in the FEM file, and I'm going to choose File, Export, and then Simulation. And here I can specify a name for the output file, so I'm going to choose saw_cover. And this is the file that I'm going to export, which will contain my mesh, so my elements, my nodes. And this is the file that Moldex3D will be able to import. Okay, so that was the first part of our demonstration. Now for the second part I will hand the word over to Larry Wren, who will show how we can use my mesh file that I just exported from Simcenter 3D in the FEA interface.
Okay, so now we are back in Moldex. We'll continue from the result that we did from the previous webinar. So this is the part. You have the two gates at the corner. You have one extra rib to remove the air trap situation. And we have a full analysis result, including fitting, packing, coating, warpage. So now let's take a look at the fitting result. The two male front meeting roughly at the center, creating a weld line. This can be seen also from this result. So you have a highlighted weld line at the middle. So we're going to export this result to structural analysis using the FEA interface function. We can choose annex nastron. We can export everything as it is, or we can choose a mapping target. So a mesh file that was pre-prepared from annex nastron, containing usually less elements. In a lot of situations, the element count that we have for injection molding simulations are just too much for structural analysis to handle, because we needed a higher resolution across the thickness. But for structural analysis, we're just using less elements, so looking at the whole situation from a macro point of view. So a coarser mesh as a mapping target will be more easier to handle. So that is to say, we're not going to export all the material cards that we have from Moldex, but with a material reduction, so that we can take the average of some nearby materials and then having less material card to be defined inside annex. We have the choices to export the warpage situation, the temperature distribution, but today we're going to focus only on the weld line. So these are the default values of the strengths of the weld line according to their meeting angles. For today's demo, we're going to exaggerate a little bit, so reducing the strengths so that inside annex we can see a clear distribution and influence of those weld lines. So now let's click OK, and let's click Export. So it's going to write some files. This will take a little while. Okay, so now we have exported the files. We can close this window. And this file will be saved inside the projects folder here, inside report, inside run one. And you have a DAT file that can contains all the material cards, the positioning, the coordinates of the weld line, and then Pascal will be able to use this file to do some further analysis inside Linux. Thank you.
Okay, thank you, Larry. Now for the final part of the demonstration, I will take the DAT file that Larry just exported and import that back into Simcenter 3D and use that to run a second analysis. And then we are going to do a comparison of the baseline simulation and the second analysis, so you can clearly see the impact the weld line strength has on the simulation results. Okay, so now we're back in the Simcenter 3D environment where we can import the DAT file from Moldex. And we can do this either by choosing import and then simulation to create a new simulation file within Simcenter, or I can choose append to merge the data from Moldex3D with our current simulation. And in this case, this is what I want to do because I want to keep my existing data and existing solution. Now here I choose to modify the existing material and element data with the file from Moldex. And then I can select the DAT file that Larry just showed that he was exporting. Click OK. Here everything is being imported. So in this case my elements get imported, my materials are being imported. I get an information window open that shows me that 52 materials are being imported. Now this number kind of depends on the on the level of reduction that was chosen within Moldex3D. In this case we chose a max reduction, so we only get 52 materials. But basically I'm still within the same file, and you can see that an extra solution has been automatically created, which was basically being done from Moldex. And what I need to do now to complete the solution, I can basically take the loads and boundary conditions from my previous solution 1, and I can drag and drop them into my new solution in order to complete my second solution here. And just to show what has been done on the background, if I click on Manage Materials here, I see that those 52 materials were created in addition to the only material I had in the library before. And these are all anisotropic materials. And if I select a material, I can see that it has a relation with a specific group of elements in my mesh. So basically each element within my mesh has its own material assigned based on the fiber orientation and a specific strength at that part of the model. So for instance, the elements that are located around the weld line location will have a material property assigned to them that has basically weaker properties than the other elements surrounding it. As my solution is now complete, I can click Solve to start my second calculation here. And as soon as the solution solver is done, I can click away all these windows and open up the results. So let's do that, and let's start by checking the displacement of the solution. Now here I can see that the general trend of the displacement is the same as we saw in the initial run. But you can see that the maximum displacement, which was previously just below 1 millimeters, now went up to 1.2 millimeters. I can also check the stress for this model, but also maybe more interesting is the strain in this case. Because if I select a strain, then you can clearly see that I have higher strain values at exactly the area where the weld line was located that Larry showed in his demonstration earlier. I can also do a comparison of the two runs, so I can put my initial run on the left side of the window, and I can put my second run on the right side of the window. And in order to do a good comparison, I can synchronize those views with each other, so I have the same point of view for both solutions. And here you can see the more than 30% increase in displacement due to the fact that the weld lines and fiber orientation is taken into account. Now if I can also put the strain here from the initial run and the strain from the second run, you can once again clearly see the difference, where there was almost no high strain value in the initial run. You can clearly see that you have some very high strain values where the weld line is located. Of course, as we've mentioned earlier, we've over-exaggerated in this case by really decreasing the weld line strength quite far. But know, of course, that when you're in the stage of really validating your design and you want to take every aspect into account, that you can use the Moldex3D FVA interface to really take the effects of the injection molding simulation process into account for your structural analysis. Okay, and that was it for now, what we wanted to show you today concerning the Moldex3D FVA interface in combination with Simcenter 3D. I would like to thank you all very much for your attention. If you have any further questions, you can always contact me directly through my email address, vasco@cardsplmsolutions.com. Okay, once again, thank you very much, and see you next time.